makes me feel.
Skinamarink. What's that one?
I heard that's a good one.
It's a weird one.
Is it?
Yeah.
Yeah.
Real weird.
All right, I'll check it out. It's on Shudder. Or
I don't remember where it's on.
okay, cool. All right, friends. So let's get on that. We were talking about permutation groups for a while, and this is kind of our last type of group study, and then things get very different after this. We don't. Our final will be a take home also. Does that sound okay?
Yeah.
I don't want to. I just don't want to come here and do a final, watch you suffer.
No, that's fine. Mark.
I can imagine you suffering in the safety of my own home.
I'm pretty sure, like, I almost cried when your email came out. I was like, church was about to start, and then you email, and you were like, you are all fine. You got a 90 to 110. And I was like,
I know. I kind of wanted to let you all know. I should have let you know earlier, but I was so lazy over break because I had those graded like on Saturday of break.
nah,
I
you're
just,
fine.
Yeah. I
No,
should. Okay.
You're fine.
I knew it would be a relief.
It was
I
a
knew
relief.
would be a relief.
I was like, okay, let's go. We all did so good.
You did. You did great. You did great. 110, Ms. Holland. I'll anti-embarrass you.
It's called having severe anxiety.
Yeah, it was, yeah, all good shit.
Kind of anxiety.
Yeah,
What's this?
I got the other one.
Yeah.
Yeah.
All right, so X is gonna be a set. Set, let's just, God, not empty, you know, there's stuff in there. So a permutation, and I'm gonna give you the most general definition. This is how it was first defined by, I don't remember who did this, but it was a long time ago, and it was our first concept of the idea of permutation. A permutation, sigma, on X is a bijective map sigma that maps X 1 to 1 and onto itself. And I don't need to put that there because I said bijective, but I'm just reiterating. It's 1 to 1 and onto. So no two things get sent to the same thing over here, and everything over here gets hit by something here. And so what you can actually kind of think of this of is a rearrangement of the things in X. So it rearranges the elements of X. And that's really what a permutation is. It's just a rearranging of things. We're not going to do, this could be an infinite set, but we're not going to do that. We're going to generally, for us, in this class, X is going to be a finite set of whole numbers 1 through n. What up, Cormac? What up, buddy? Where you at? Hope you watch this. We miss you. I brought your plant today.
I was gonna say.
Shh. Don't tell him I didn't bring the plant. All right, so I'm gonna give it to that guy across the hall. So for us, X is just this set of integers. And what we're gonna talk about is this collection of maps, S sub n, which is the set of all sigma, such that sigma is a permutation on this X right up here of n elements. And in general, it's kind of convention that these lowercase Greek letters are used for permutation identification. So we're gonna have some fun with that. So like, what do I mean? Well, let's make something chill. Let's say X is just 1, 2, 3. Then I have this sigma, good Lord, in S3, and it's S3 because there's 3 things here, is going to do something like this. It's going to take 1 and spit out something, 2 and 3, And it's just a permutation of these three things. So for example, this guy right here is a great one. It sends 1 to 2, 2 to 1, and 3 to 3. You can think of this as rearranging. You can think of this as taking this set and flipping the 1 and the 2. Even though this isn't an ordered notation here, you could think of it that way: first slot, second slot, third slot. So it's kind of doing this. This is called a transposition. I'm just taking two things and flipping them.
That's what we did with we did similar things with the triangles, right?
Yes, yes. This is directly related to the dihedral stuff,
Oh,
yes, the
okay.
D3. And we'll actually take a day to just talk about those dihedral groups.
Mhm.
So we're kind of abstracting even more from that. We're taking that idea and pulling back to a higher level, and then we'll come back down to that level. So this actually is, yes, the symmetries on a triangle, this guy here. And I think I mentioned that back when, but now we're not gonna think about the triangle. We're just thinking about the permutations of this all. So another way to write this sigma, and part of today is just kind of getting this notation down and working with it, is, ooh, that's so good. I'm gonna write this matrixy looking thing. It's not a matrix, it's permutation notation. So the top row is the original set. And then the bottom row is the permuted version of that. So this guy right here would look like this. The 3 just got mapped to the 3. These mean the same thing. Bottom is permuted set.
So is S sub n, that is the permutation group of its words.
Yes.
So does that like still adhere to like the idea that there's like an identity?
And I'm gonna prove all that. Yeah, exactly. Yeah, it'll turn, this is actually a group under composition of permutations.
Okay, okay.
Yeah, and we'll prove that. That'll be one of, I'm not gonna prove, there's some things I'm not gonna prove because they're so gross I can't even stand it.
Fair enough.
Yes.
So if it's a group under composition of permutations, does that mean its order is the number of times you could permute something?
Yeah, the number of permutations.
Yes.
Yes, yes.
Okay.
Yeah. And we'll get there too. That'll be something else we'll look at.
Okay.
You probably already know it. So we've got this notation. Let's see, what else did I want to say about that? Oh, I guess I'm getting to your questions right now. Let's prove it's a group. Let's prove its order is what? What do you think the order of S of n is?
And
Is it 3?
Okay. So let's do S4. All right, I've got 1, 2, 3, 4 slots. How many ways can I fill the first slot?
4 ways.
4 different things can go in there. Now I've set that. Now how many are left for that?
3.
What's the number of combos of this?
24.
Yeah, we multiply those all together. So 4 factorial would be the actual number of things in here. Right? If I got 4 pairs of socks, 3 pairs of pants, 2 shirts, I got 24 outfits. I don't have 24 outfits, as you know, but someone could have that many. So this would be 4 factorial arrangements. Does that make sense, Christian? I saw you
I think
maybe.
I'm getting a little bit lost there. So I thought order was just like the amount of elements, right, in a set.
So this is the number of ways I can permute the set X.
Okay.
And every permutation in that, in S4, is going to be how many different rows down here could I have?
Okay.
So how many places could I send 1?
4 different.
Yeah, 4 different ways. So there's 4 ways to fill that slot. And then when I fill that slot, I can't repeat entries because it's a bijection.
Okay.
So then I've already picked this, say I picked 3 here. Now I've got 3 more things.
Oh, okay.
And so 4 there, and then I gotta use the remaining 3 for that. And you see now?
So like the subscript is referring to like the number of elements?
Yes.
Right? Not the
Not the
number
order.
of permutations. The number
Correct.
of permutations is the
Yes.
Okay.
This N is, yeah, and I tried, I should have made it
I
a
see
little
what
clear.
you-
If I
yeah.
put a little sub N there, that might make it a little,
I see what
Is
you're
that good?
Yeah.
So for S sub 3, it would be 6, it would be
Yes.
order 6.
correct,
Okay.
yes. Does that make sense, kind of so far? So, we'll write it up as a formal result, here in just a second. So let's prove it's a group though. And its order is n factorial. So theorem, really the only thing I'm going to prove today, S sub n is a group under composition of permutations. And I think I might actually just talk about that for a second before we get into the proof. And its order is n factorial. So let's talk about composition of permutations so that you have a more intuitive sense of what I mean there. And these are functions, right? These are functions. They're maps from one set back onto itself. And so I can compose them like I compose functions. Well, let's actually look at some specific examples. So, example of composition of permutations. So let's work with S. Let's do S4 for something a little bit more interesting. And let's say I've got sigma and tau that are in S4. That's element sign there. So I'll be more specific. Sigma is going to do 1, 2, 3, 4, and it's going to move 3, 4, 1, 2, like that. It's kind of a shift, kind of like shifted things, wrapped them around. And then let's say tau is just a permutation, a transposition of 1 and 4. So it's going to send 1 to 4, 2 to 2, 3 to 3, and then 4 goes to 1. Composition symbol is its functions. And we use that little open circle for these. You could, this is cool too. I'll know what you mean, you'll know what you mean. You should, just as long as you know what you mean by that. That means compose. First, second, right? Because function composition. This goes first, and then this is second. So let's actually put those things together. So 1, 3, 2, 4, 3, 1, 4, 2, composed with 1, 2, 3, 4, 4, 2, 3, 1, equals another permutation. I'll initialize it. Stop for a second, let you get caught up. Feeling really good today. This is like very, very clear-headed, pretty energetic. So the way I chase this down is I say, where does 1 go? Well, 1 goes to 4, but 4 goes to 2 then. See how I did that? Can you fill in the rest to make sure we've got some sanity going on in the room? Finish up the last 3. I spent so much time working with these things over the break. This was my recreation over the break, besides like killing things in Borderlands. Exactly. It's like, when I wasn't killing things in Borderlands, I was permuting things. Let's see, so 2 goes to 2, 2 goes to 4, 3 goes to 3, 3 goes to 1, 4 goes to 1, 1 goes to 3. Sound good? Let's do it in the other order just to like make sure that we know for a fact these things do not commute in general, and I think that'll be the case here, but I kind of want to see. So here I'm going to put, this is going to be tau sigma. 2, 3, 1, 3, 4. Yeah, let's see what we get that way. Definitely not the same.
That one's weird because that just came back out as sigma.
Wait, did it?
Yes.
No, I think you're looking at.
Oh wait, 1 and 4 is false.
Yeah, that scared the shit out
Sorry.
of me, because
Yeah,
that
that
can't.
scared me too. I'm like, I don't
Because if that's
understand.
happening, all the time I spent, I should have just blown things up in border lines.
No, I just can't look at it correctly.
You're cool, we're good.
We're cool.
Awesome,
I even wrote it down right too. It's just like in my brain.
it's all right. We good?
Mhm.
Everybody cool on these computations? Abraham, you good?
Believe so.
Okay. Mr. Gilmore.
Oh boy.
All right, let's prove this thing, now that we understand what's meant by composition. So we're gonna prove this is a group. What do I have to show?
You have to show the identity element.
Let's get the low-hanging fruit, right?
Yeah.
Low-hanging fruit. So to show Sn is a group structure, identity. What's the identity element in here? What is the identity? So I got phi that goes from this set x sub n, that's the 1 through n, to x sub n. I like that note. I'm glad you actually said something, Christian, because I think that kind of helps. What's my identity?
So like the not moving anything.
That's right.
Just be 1 to 1, 2 to 2, 3 to 3, 4.
It's literally the identity function. Yeah, so you're right, it leaves everything alone. Take x, spit out x. Or, if you like the other notation, and actually, sorry, there's a special notation for this. It's epsilon. Instead of e for our identity, we use epsilon because we're Greeking out. And so epsilon, the identity here is 1, 2, 3, up to n, and it just sends those things to themselves. That's another way to look at it. So this is a very different kind of proof than we're used to. We're literally just like, oh, there's an identity, here it is. What else do I gotta show?
Closure.
Closure, let's do that. So I've got sigma and tau and S sub n. Y is sigma tau and S sub n. What does it mean to be an S sub n? What does that mean? Go back to the primal definition. It's not on the board anymore.
It's a bijective map.
Yeah, bijective map from the set 1 through n to itself. So 1 to 1 and on to. This is 1 to 1 and on to. This is 1 and 1 and on. 1 to 1 and on to. Composition of 1 to 1 maps is 1 to 1. Composition of onto maps is, composition of bijections are bijections. We're copping out. That's not a cop out. That's like super high level cop out. But because composition of bijections are bijections. Yay! Nice, sweet proof. And we're gonna stay on this side of the board. We're gonna get done on the left side. What else? What's the last thing? Inverses. So take sigma in S sub n. Y is sigma inverse in S sub n. Why does sigma inverse exist? What do you need for an inverse to exist?
Oh, it needs to be bijective.
It's
So-
gotta be it's gotta be a bijection.
Oh, right.
It's gotta be 1 to 1 and on to.
Yeah.
So because this map is 1 and 1, 1 to 1 and on to x, its inverse exists and must map to the same place. The domain and range are both x here. So because Sigma is bijective. That implies sigma inverse exists and is bijective, and it maps x to x. So sigma inverse is back in S sub n. Cool, that's it.
Well, wait.
Yes, sir.
Associativity?
Oh, right, yes. Shit, put it over here. And associativity, right, because we're not doing the subgroup test, right?
Yeah.
Yeah. Well, it's high level cop out again. Composition of functions is associative. It just is. So composition of functions is associative. And we have functions here. So good shit. Done. And then let's do the last part, the order thing. Lastly, order of S sub n is n factorial. I've got sigma 1 equals, so if I've got sigma in S sub n, and sigma does this, I'm going to use this notation just to play with it. How many different outputs could I put here?
You could put n outputs there,
N options,
and that would be n minus 1.
and n minus 1, and n minus 2. Yeah. And then it's called the multiplicative proper principle of counting or something like that. If I can do this x ways and this y ways, I can do them together x times y ways. Pretty reasonable thing to do. I don't need to talk about my wardrobe again. So here's n minus 1 options. And then I get down to the bottom, and this last one's determined by the previous ones. Whatever you haven't picked yet is that last slot, last assignment. So here we have n factorial ways this can happen. And since there are n factorial ways this can happen, this happening is a permutation, so there are n factorial permutations. And Christian, you feel okay about that now?
Yeah. Yeah. I
Yeah,
don't know.
okay, yeah, I can.
feel like super formal, but I mean that's fair. I'm with
Yeah.
that.
Yeah, it's not super formal.
Yeah.
I'm not doing that.
That's
today.
cool. Yeah,
Okay.
no worries.
Okay. Any subgroup of S sub n is called a permutation group. So we're gonna have little groups inside here, and then sometimes you just have a subset of these things, and that's just called a permutation group. I'm not even gonna write that down. It was just a note I had to myself. But let's actually look at a little example of a S sub n, I'm gonna call it a subgroup because that just makes more sense to me. And we're gonna call this group just the set, so we're gonna have the identity, and then we're gonna have, and actually, sorry, let's do S5, apologies. So we have something to hold on to. And then we have a sigma, and we have a tau. And sigma, oh shit, I got 3 things in here. Mofo, sigma, tau, mu. STU. Yeah. Oh, I didn't even, yeah. Okay, alphabetized Greek-wise. So I've got this little group here, and I'm gonna tell you what they are. So this is the identity, but sigma is 1, 2, 3, 4, 5, and it goes 1, 2, 3, 5, 4. So it transposes 5 and 4. We've got tau is 1, 2, 3, 4, 5, and then 3, 2, 1, 4, 5. And then lastly, we've got mu is, I'm just gonna write the bottom row, 3, 2, 1, 5, 4. Oops. So it transposes the 4 and the 5 and kind of rotates these 1 through 3, cycles them. So anyways, you gotta there's lots of interesting things that can happen with permutations. You see like a cycling on these first three elements, and then just a swapping of these last two. And you can kind of describe this one as just a cycling, a slightly different cycling here. You just moved that 3 to the front, you left these guys alone, and then here you just transpose the 4 and the 5. But from these are actually closed under composition. So if we have composition here, and down here I put epsilon, sigma, tau, mu, epsilon, sigma, tau, mu. How's our time going? Time's going good. I feel like now might be a good time to show you a better notation. Because we're gonna need to compute all these things, and it's gonna kind of suck a little bit with that notation. It's a little clunky, so why not introduce the thing I was gonna introduce anyway, which is cycle notation. And I was kind of hinting at it just there.
I think you showed us cycle notation when we did the hero groups.
I think so, yeah. But let's talk about it again.
Yeah, I need more practice.
Okay, yeah, I'm not gonna skip the.
Yeah, please don't skip that.
No, don't worry. Yeah, I did though, I did mention it, but it was only like to plant the seed, early, knowing that we'd be back to visit. So let's talk about cycle notation. Because it really makes computing with these things so much better. So cycle notation gets you out of this 2-row scene you have here, because this is really pedantic and pointless. Everybody knows what's on the top row. Once you know the top row is 1 through 5, you have to write it every freaking time, no thanks. So this gets this whole system down into a single cycle. So I'll show you how to do it. So sigma, and then I'll come back to epsilon as a little special treat. So I'm just going to use a left brace, and I'm always going to start with 1 and see what happens to 1. So 1, well, oh shit, 1 just goes to 1, right? So 1 didn't go anywhere. Close it off. Then 2, what happens to 2? Whoops, I think I cheated.
2 doesn't go.
2 doesn't kind of do that. And then 3,
Same thing.
same thing. What about 4?
Goes to 5.
4 goes to 5.
5 goes back to
And
4.
5 goes back to 4, and this is a wraparound notation. So when you spill out of one side, you come around to the other. It's a wraparound screen. So if I had 1, 2, 3 here, what this means is that 1 goes to 2, 2 goes to 3, 3 goes to 1.
Could you rewrite your sigma, or could you leave out the 1, 2, and 3?
Yeah, that's what I'm gonna do. I just wanted to do it for our first time through. But yeah, these are very uninformative.
It's very trivial.
So they're trivial. We don't write these trivial ones. So I'm just gonna say sigma just swaps 4 and 5, and that's the essential detail. Why write the other shit you don't need? It transposes, so this is a transposition, 4 and 5, and that's all it does. So why not just record that? Can you do tau and mu? I'm tasting blood. That's not good.
That's not good.
That's not good. That's not good. So if I black out, just throw something so I don't hit my head on a corner. Or call for help.
That might be better.
That might be better. So class is dismissed. I think you're gonna see how nice this is just by trying it, right? It's really pretty and compact. Wait, so tau 1 to 3. And then you kind of chase it down. So just so you see, so 1 went to 3 and 3 went back to 1. So notice how I chase out that cycle, because it sends 1 to 3, then you go look, where did 3 go? And you put that next, and 3 just goes back to 1 on that guy.
So basically you just follow it until it dies.
You follow it until it dies, but you make sure to address everybody inside there. Is that what you were gonna?
So it has to die like back on the start.
Yes. Yeah, what?
I was just like, if 3 didn't go to 1 over there, like let's say it went to 4, then we go to 4, like, do you know what I'm saying?
Yeah, I think this guy will be a good example of that. I think, yes, we would keep going.
Okay.
We would keep on putting the cycle, but now I'm just gonna check out 2 and make sure. 2 goes to 2, so I didn't need to write that. Nothing else happens here, actually, right?
Just leave it at 1, 3.
Just leave it at 1, 3, because that's all it did. is
But if it
swap.
was like 3, 2, 4, 1, then you'd have to continue that change.
And I think this guy's gonna do that for us. I think, no, it's not.
No.
No, it's 2 separate ones.
Oh, is it, oh,
One
at least
is
it's
for your
2, at
thing.
least it's 2 things,
It's
right?
like 1, 3, 4, 5.
So it's like this?
Yes.
Okay.
My question is, what if you have something that doesn't circle back around? So like, what if 1 went to 3 and then 3 went to 4?
Eventually you would have to cycle back around, so I could, in S5, I could have something like this that goes 1, 3, 2, 5, 4. So this would look like this. It would send 1 to 3, 3 to 2.
No, it'd stay 1 to 1.
Or no, it would
What?
go
Because it's
That'd
1,
be
3.
1 goes to 3.
Yeah.
Oh, 1
3
goes
goes
to
to
3.
2.
Gotcha. Sorry,
Yeah,
I
yeah,
thought you
it's
were
okay.
writing out the.
Oh, no, no,
what
no.
it would've been.
Is this cool? You with me?
Yeah.
Cool. And then 2 goes to 5.
Mhm.
And then I gotta go, and then 5 goes to 4. 4 goes to 1.
So you would never have a scenario where there isn't something that like fully loops around. It's closed, right? It has to.
Like what? I think I'm not understanding what.
Yeah, I think so. Like, I'm saying, what if you had 3 of them, right? And 1 went to 3, and then 3 went to like. Oh, I guess you couldn't.
Like,
because,
so it's not
3
a
pointed to
cycle.
2. Yeah, but
It
that's
wouldn't
not
be
a
a
cycle.
permutation.
It's-
It wouldn't be a permutation if you didn't. Yeah, it has to be on to, right?
So the nature of it will always
Yeah.
look back around somewhere.
Yes.
Okay.
Yes. In fact, one of our results that I'm not going to prove is that literally every permutation can be written as a composition of disjoint cycles, like this. So you can take any permutation and write it as a composition of cycles inside the elements, which we will see in a bit. Christian, do you have a question about that? You're just like processing it.
Yeah.
Okay, cool. So look at how much better this is gonna make this shit. So let's just do a few let's say this is for, let's say, so, we'll call this top and call this left. And let's make sure we understand which way we're composing. So I'm gonna do, the left first and then the top. So this, then that. You could do it the other way, but we just need to establish who's the right. Oh, here, sorry. What if we just make this left and make this right? There we go, sorry. So this actually goes first, not here, yeah. But that's just clear. What do you think this top row is gonna look like?
Epsilon
Epsilon? Identity composed with anything?
itself.
Itself. Doesn't matter. You do the composition, or you do the permutation, and then you leave everything alone. Or you leave everything alone, and then you do the permutation. Either way, good like that. So now let's do sigma squared. And I want you to watch this. So this is good. So sigma squared is 4 goes to 5, then 5 goes to 4. So I just follow it twice. So what is sigma squared? It's just the identity, 5, because then 5 goes to 4, 4 goes to 5. So it's just the identity element. Let me put that here, and then you tell me if that needs extra talking.
So that means tau and tau is the identity. Like it's gonna go straight.
Yes, yeah, because each of these is actually just transposing of elements. When you do it again, it just puts them back. This takes 1 and 3 and flips them. When you do it again, it flips them back.
Oh.
Does that make sense?
Yeah.
So also tau, yeah, that's great. So tau squared is epsilon and u squared is epsilon. So we've got this pretty epsilon down the side. Looks like we're looking like the Klein 4 group, if that makes
Right.
you.
Oh, I thought it was gonna be the order 4 cyclic.
We're not cyclic because these guys only have order 2.
Okay, you're right.
Does that make sense?
Yeah.
And it's the other one.
That
That's
makes
how I know
sense.
that. It's the other order 4 group. So let's do sigma tau and sigma mu. And then I'm going to show you how we finish up. Let's find these guys. Sigma tau, sigma mu, tau sigma. And then I think if we get these, we can kind of like cheese out the rest of it. Because it's a Cayley table, and since it's a group, everything appears exactly once in each row and column. And we're gonna Sudoku this thing, you know, and kind of. So let's see, this tau goes first, 1 goes to 3. I gotta write it out. So just 4, 5, 3. Which one is this?
Can you explain how you're doing that? That's a bit of a leap.
Yes.
Okay.
Well, literally, right now, I'm just writing down what they were.
Oh,
So sigma was 4, 5, and it's on the left, and then tau was 1, 3. I just literally replaced these with their formula.
so that's actually the same thing as tau composed with sigma, right?
Yes.
Okay, so you're okay, got it.
So check this out, and this is a really important point. These are disjoint transpositions, so you can do them in either order. Flip the first and third thing. That doesn't touch the fourth and fifth thing. So this motion is completely separate from this, so it doesn't really matter what order I put these in. 1, 2, 3, 4, 5. So if I flip 1 and 3, and then I flip 4 and 5, I get this. But I could have done that in the other order, and I would get the same thing, flip 4 and 5, then flip 1 and 3. Looks the same. So disjoint cycles commute. That's like one of our results, but let's just make a little note of it. Disjoint cycles, and they're the only ones that commute, are the only elements that commute. Because otherwise they share some common thing and it gets moved by one and then moved by the other. Only elements that commute. So what guy is this? Sigma tau is what? It's mu.
That's mu.
It's mu. It's mu. And in the other order, it's also mu. Because I could have written mu in a couple orders. Let's just make a little note here. Or it's 4, 5, 1, 3. Doesn't matter. Same thing. Are you getting a feel for this?
Yeah.
Starting to get some intuition. Cool. That's what today is supposed to be about. What goes here? If this is a group, it is a group.
It has to be tau.
Got to be tau, and tau, because everything's like disjoint here. What goes here?
Sigma.
Sigma. There we go. And we could verify that if we wanted.
So,
Yes.
like, sigma composed with mu is the same thing as mu composed with sigma,
Yes.
but those cycles aren't disjoint, no?
No, but these parts are. So let's look at that.
See what I mean? Like, 'cause
I know what you're saying. Yeah. Sigma. So this we do maybe have to check, but if you look at it, Christian, all this does is undo this guy
yeah.
and get you back to there, right? So,
I guess what I'm asking is, does it hold the disjoint cycles? Or
Actually-
the only elements that commute? You know, because those aren't disjoint.
Yeah. How about that? Yes, sir.
So if we had that one down there, the 1, 3, 2, 5, 4.
Yes.
How would that map with something like sigma?
Okay, so let's do, let's call this, let's write it in
I was
cycles.
gonna
Oh,
say,
I already have it.
like gamma or something, and then.
Yeah, let's call that gamma, and then if I had like gamma sigma, like that. So let's see, so that's gonna be 1, 3, 2, 5, 4, and then sigma is the, well, 4, 5. And these definitely aren't gonna commute, for sure. I think probably, transpositions commute, Christian. I
Okay.
think transpositions
Yeah.
commute.
Yeah, there's-
I just, yeah, but to be safe, we'll just say that for now. So let's see, Abraham, then what I'm gonna do is go from the right. Where does 1 go? So I'm gonna start with 1. I'm gonna say, where's 1 go? This guy doesn't touch it. This guy sends it to 3. Where does 3 go? Doesn't touch it, 3 goes to 2. Doesn't touch 2, 2 goes to 5. Now we got some interaction. 5 goes to 4, but then 4 goes to 1. You
So
have to fit, you gotta go through the pipeline.
So does that close it off then?
Yes,
And then 4 just goes to 4 and that's it?
and then, yes, and then 4 goes to 5, which goes back to 4. So we could even, if we wanted to just let everybody know we addressed it, put that there. Does that,
Okay.
I kinda wanna do them in the other order. Let's just do it while we're here, cause honestly, like, this shit is fun. It's pretty chill. 4, 5, 1, 3, 2, 5, 4. Start with 1 when you're doing these compositions. Unless you don't see 1 mentioned at all, then you know it just
Just
stays.
ignore it.
Ignore it. 1 goes to 3. So far, so same. 3 goes to 2. 2 goes to 5. 5 goes to, well, these do commute, don't they? Is that right?
Yeah.
Yeah, they do commute. 5 goes to 4, but then 4 goes back to 5. And what happens to 4? 4 goes to, wait a minute. Wait a minute. Wait a minute. What am I doing wrong here? Hold on.
5 goes to
5 goes to 4.
4, which goes to 5, so 5 stays with 5. Wait, no, sorry. No,
Oh,
5
5
goes to 4, no, because like 5 goes to 4, so if you go look at the other 4,
That 4 goes to 5.
that 4 goes to 5.
But then you
So
gotta
5
go
goes
Oh,
to
back
five?
that means, oh, wait. So wait, okay, hold
Hold
on.
on.
Hold on, what the fuck? Okay. Alright, 1 goes to 3, that's for sure.
Yeah,
3 goes to 2,
for sure.
yeah. 2, oh, 2 goes to 5, which goes to 4. That's what I fucked up. Is that better?
Yeah.
Yes. 4 goes to 1, which closes it off.
Yeah.
Now I'm closed off. And then 5 just stays fixed.
Yeah, 5 goes to 5.
5 goes to 5.
And would that be the same for the one before? We would just swap the 4 and the 5, or is that one?
This one's right.
Okay,
This guy's right.
so it's a different order?
Different order. Yeah, so they don't, these are not the same permutation.
But you always start with the one on the left and see if it fits in there first, and right?
One on the
Oh, no, sorry, the one on the
right.
right.
Start on the right.
Start on the right.
Think composition of functions, right? The guy on the right
Yeah.
does
always
stuff
start on the
first
right.
and then everything moves off of that. How's this feel?
Can we do a practice one?
Yes.
Like one for us to check ourselves.
Can I show you something else first?
Yeah.
Because this like, you'll be, we're gonna do plenty of this
Okay,
stuff.
okay, cool.
And with the work with it. I wanna give you a theorem I'm not gonna prove from the book. The theorem goes like this. Theorem, and I'm gonna show you how to compute it, but I'm not proving it. Theorem, every permutation on a finite set can be written as a product of disjoint cycles. And I alluded to this. I'm gonna show you Well, actually, you're gonna get your practice, Sophie, as a product of disjoint cycles. This is key. Proof left or reader? Go read the proof. Proof's in the book. Let's do it. Example, e.g. I've got this beastly permutation, 1, 3, 2, 7, 4, 5, 6, 8, 1, 2, 3, 7, 6, 4, 8, 5. And this is like a homework problem. And that's why I say your homework is pretty chill. Because all we have to do is chase this thing down. First off, where could this be from? S what?
8.
8, right? 8's the highest number. So it could be from a higher, right? It could be from S9 or 10, but this at a minimum, it's in here, at a minimum. But it doesn't matter, because we're gonna just chase everything down. So start with 1, read from the right, what comes out the left?
7.
Let me see, let's do a sanity check. 1 goes to 2, 2 goes to 7. 7 doesn't get touched, I agree. Then chase down 7. And then do that until you wrap back to 1. And then you close off that cycle. Then 3? Okay, cool. Just keeping it sane. And 2. And then close. So you have a 4 cycle. And then just pick up with
4.
Yeah, 4 next highest, sure. It doesn't really, yeah, just grab one you haven't done yet. 4 goes to 5. 5 goes to 4, 6?
Yeah.
Okay, cool. 6 goes to 4.
5.
Wait. 6 goes to 4.
And then 4 goes to
4 goes to 5.
And then 4 goes, oh, gotcha. 4 goes to 5. And then 5 goes.
5 stays with itself.
5 goes to 6, which goes back to 4.
Yeah, so it's closed.
See that, Sophie?
Yeah, I guess I was confused by the 5 being isolated at the very end. So you pick the first one that is not.
Well, yeah, this guy just doesn't do, it's like
It's not doing anything.
5, I
Just
just,
pass
through.
5 stays 5.
Yeah.
Really uninformative.
And then 8 just stays 8.
Probably. Are we at the?
We're just at 8.
Cool. Yeah, that sounds right. I kind of almost has to, because here I've got 7 things already,
Yeah.
and there's only 8 things up
You
there.
just go over how you went from 7 to 3. I think.
Yep. So 7 goes to 1, wraps around to 1.
Okay.
1 goes to 3.
Okay, so if it's at the end of a bracket, it just loops to the
Yeah.
first one?
Wrap around.
So the 5 there loops back to 6, and then.
Yeah, exactly.
And 6 goes to 4, 4 goes back to 5, and
Yes.
stops, okay.
Yeah. Feel good?
Yes.
Wait until everybody looks like they feel, yes, no, they're good, okay.
I guess
This is the man who doesn't look like he's good.
So just the disjoint cycles thing.
Yes, sir.
What is a disjoint cycle? Because like it can't be that they just don't share any elements.
That's exactly what it is.
Well, okay, then like what about like the 2, 7 and then 1, 2, 3?
Well, these
7?
aren't disjoint, but we rewrote it as a disjoint cycles. So this process that we just went through, Christian, takes stuff, these aren't disjoint, I agree.
Okay.
But if after I go through this process, I end up with disjoint cycles.
Okay.
So by computing the permutation, it ends up as disjoint cycles.
Okay,
As disjoint as they could get at this point.
okay. Fair enough. I think it's the wording in the theorem that's kinda
Yeah.
like tripping me up.
And these guys do commute. Like
Yeah.
all disjoint cycles do definitely commute, because they don't touch the same things. They're just kind of working over here and working over here.
Okay,
But this is the process to take any composition of permutations and turn them into disjoint cycles.
okay.
Which is one of your homework problems.
Yes.
Probably the one where it's like A through whatever, do this a lot.
Would it be like the same if you were gonna say like the product of permutations on a finite set is always a disjoint cycle?
It can be written as a product of disjoint cycles. It's not a single disjoint cycle. Well, because that doesn't make sense to talk about disjoint things.
Okay, yeah,
Yes,
yeah, yeah.
there you go. Okay, yeah,
Yeah.
that helped, right? Okay,
Yeah.
yeah.
I was getting caught up with it because like it felt like you were saying like the product of disjoint cycles is in like the result of multiplying disjoint cycles.
No, that's why I was really clear, like,
Yeah,
these
yeah.
aren't disjoint,
Yes,
but I
yeah.
created.
I see what you're talking about.
Yeah, I distilled it
Yeah,
away.
that
Yeah,
makes
yeah.
sense.
Good? All right. Let's talk about doing some things with this. So, let's talk about a cycle. If I have a cycle, this is some theorem, I don't know what it is, I'm just like fucking making it up. It probably isn't a theorem, it's just like what we're gonna write. If I have a cycle, A1, A2, down to A sub K. K things. A1 goes to A2, A2 goes to A3, AK goes back to A1. If I have this, the order of this is the number of elements in there. It's the length of the cycle. The length of a cycle is the order of the cycle. It's how many times you have to compose it with itself to get back to the identity. So let's see that. This should be order 3. 4, 5, 6. Now I'm going to show you a cool thing that I learned on the couch over the weekend. If I want to compute this square, watch how cool this is. I never knew the stuff I learned over the weekend before. Like, I'm all over permutations now in a way I never have been. Think about what it would mean to square this. You would send 4 to 5, but then you'd send 5 to 6. So in essence, you're sending 4 to 6. Notice how I skipped the power of elements. So to square it, I just skip 2 elements ahead. 4 goes to 6. 6 goes to skip the 4, 5. 5 goes to skip the 6, back, oh wait. Yes, back to 4, yes. If I were, and I could take that from there, but what if I wanted 4, 5, 6 cubed? Then I would skip 3 elements.
So that's just itself.
It's just itself.
But if it's order 3, then 4 is 4. That makes sense.
Yeah, check it out. So here 4 goes skip back to 4, 5 goes back to 5, 6 goes back to 6. It's the identity.
So if you square it to its order, you'll get the identity.
If you power it to its order.
Oh yes,
yes,
power
yes,
to
yes.
its order.
Mm-hmm. Yes. But that's the quick way to raise power. So like one of the problems you get is raise this permutation to the 100th power. For the love of all that's holy, do not compute that. Don't write it out 100 times. What's this? To the 30th power.
Is it just the identity?
It is, because raising it to the 3rd power is this, and then raising this to the 10th. So if I said put this to the 30th, that's just this to the 10th. That's just this. Be savvy on the things, right? So for example, what about this guy? What about 1, 3, 5, 2, 4? First off, what's the order of that permutation? 5. And I can prove that by saying, raise it to the 5th power, I skip ahead 5 elements. 1 goes to 1, to send everything back to itself. What is the inverse of this?
4, 2, 5, 3, 1.
How'd you get that?
Backwards.
I don't know, let's find out. I don't know about that. That wasn't something I discovered on my couch, but it would be this to what power?
It's the negative.
The 3rd power,
What?
or no, sorry, the 4th power, right?
Okay.
The 4th power of this would be 1 less than the identity, but the thing with powers works backwards as well. So instead of moving ahead, I'll just move backwards. So this is gonna go 1, and so the only thing I would just recommend is maybe just keep these things in order as much as possible, in magnitude order.
Yeah.
So 1 goes to 4. See how I went backwards 1?
Yeah.
Oh.
And 4 goes to 2.
4 goes to 2, 2 goes to 5, 5 goes to 3, 3 goes to 1. What if I asked you to do, you're so set up for your homework, quite honestly. But we're almost done, we got one more thing we need to talk about. What if I had 1, 7, 8, 2, 3, 5 to the negative 2 power? So the inverse squared.
It's 1 goes to 3,
1 goes to skip the 5, go to 3.
7 goes to 5.
And then I would work from here,
3
right?
goes to
Oh,
So
sorry.
3 goes to
3 goes to
8.
8.
1, so this is
8
closed.
goes to 1.
Yep, closes off.
And then you have like
And we continue
7
with
goes to
7.
3.
Might as well, yeah, we could
Or
probably
7 goes
want to go to,
5.
maybe we'd go to the 2 just to like keep magnitude. You could, it's fine. It's no big deal.
Well, you get to 7 there.
Yeah, then you get, yeah, exactly. It's just a step away. And-
Goes to 5.
Do we have anything else?
7 goes to 5.
Oh, 7 goes by, I got a little excited there.
And then
Yeah.
5 goes back to 2.
Cool, thank you.
And that's all of them.
That's it. Isn't that cool? That's shit I never knew. No one ever showed me that. I was like, is this real? Is that real? What's happening here? So, let's talk about one last thing that you need for that homework. The order, this is some theorem, the order of a product of disjoint cycles is, and let's see if we can reason it out ourselves. Let's say I've got some disjoint cycles over here. Let's see if we can figure this out. All right, so this goes 1, 2, and then I've got 3, 4, 5. So here I've got some permutation, and I want to find its order. What's the order of this piece?
2.
2, order 2. This is order what?
3.
Order 3. When do they sync up? So this is syncing up every power of 2. This is syncing back up every power of 3. 6. What do you call that? What is the relationship between 2 and 3 and 6?
6 is the least common.
Least common multiple. So it's always the least common multiple of the cycles. The order of sigma is the LCM of 2 and 3, which is pretty easy, 6. And let's see, what do I want to say about that? I just kind of think, while we're here together, let's look at 8 and 9 on the homework together. Because I kind of think I've said what I need to say, and those are the 2 hard ones. So while we're here together, can someone look those up for us? Camila's like always got the shit like right there. There it is. Oh, you have it too?
8 is show that A10 contains an element of order 15.
Okay, so, oh, A10, shit, let's take that problem off,
Oh,
cause I need to talk about A.
oh, okay.
Take problem 8 off, that's good,
Nine
that
is
helped.
also an A question.
Then I guess we're not doing 8 and 9 till Monday.
That's awesome.
Sounds
So
sweet.
it's just 1, 2, and 3 in most sets.
Why don't you check them out while you're here and get going? You might be done by the time you leave.
You think it won't take more than 10 minutes?
I don't think it's gonna take much more.
I'm surprised they fixed that clock.
Oh, did they? Oh, that's right.
That's what I'm the most surprised about.
That is shocking.
Yeah, but the lights just do some weird, like, satanic things.
There is.
You know, baby steps will take it.
Ooh, don't say baby steps when we're talking about lights going on. Oh, that's creepy.
We can call the
Baby one.
priests to do an
Little
exorcism.
ghost.
No, I mean like in terms of them fixing one little thing at a time.
Oh, you're not talking about ghost babies.
No.
Okay, that's good. That's scary as fuck. Your little pitter patter in the ceiling and the lights go off. Yeah. And I mostly wanna make sure I gave you enough info to do those, and I think I did. Does everybody have access to the problems? Cause otherwise I can help you. Everybody's good. Yeah, should be good.
Is a permutation the same thing as an isomorphism?
No.
Because okay.
Well,
I think you're
No.
right, because an isomorphism has to be on a vector space.
or yes, it has to have a structure, so an isomorphism preserves like an algebraic structure.
Okay, I guess I'm curious because like an isomorphism would also be defined as a bijective map.
Yes, that preserves the group structure.
Yeah.
So for example, that group, when I took this thing up here, that is isomorphic to the Klein 4 group. So when we talk about isomorphisms, it has to be an algebraic structure primarily.
Okay.
And it says these essentially are the same, just the symbols are different.
Okay.
Same for kind of the same. Vector spaces get a little, but they could be treated as the same.
Okay. So then just like an isomorphism in like the abstract algebra sense means something slightly different than in like the linear algebra sense?
Not really, it's just you have more structure to preserve in a linear space.
Or in like the abstract space?
Well,
Because like in the abstract space, you would need to preserve like that's
when you say the abstract space, what do you mean?
like kind of with
A group.
this.
Group.
Yeah, like,
So there's less structure, all we have to do is preserve the group product.
okay.
That has to work the same. So here, let me be more precise. If I'm more precise, this will help. I've got a group G and a group H, and I've got a map that goes between them, and it has to be a bijection, because it has to,
Yeah.
but that's not enough. If I have the operation here is star, and the operation over here is circle, then phi of G composed with G star H. So if I take two things out of G and compose them,
Okay.
and then look at the image under this map, it has to be the same thing as the product of the image of G with the image of H.
Okay.
In a vector space, you pretty much just have multiplication and addition, and you have to preserve those. So like, in a vector space, in a vector space, you would have like phi went from V1 to V2. You have to preserve that linear structure, so there's a lot more that has to be preserved here. It's not just, I have to have phi of alpha V1 plus beta V2. That has to go like this. So in other words, I've got these two vectors here in this space. I've got V1 and V2, and that's in V1. It's bad, not great notation, but, and then I take those and I run them through phi, and over here, Phi, maybe phi is just even like a rotation or something. Doesn't necessarily even have to be, I think, I don't know, it doesn't necessarily have to preserve angles, but this would be like phi of V1, and this would be phi of V2. And so what this is saying, Christian, is that this linear combo here is this guy, right? It's something. It's not, this is just alpha's 1 and beta's 1, but you get some vector that comes out of there. So that's that alpha V1 plus beta V2. And that has to get mapped to the same place that these two combinations would produce. So this has to go there as well. It's the kind of the same, but there is more structure to preserve here. It's harder to be this than it is this.
Okay.
So there's a natural here. I could map phi from this group G to the Klein 4 group. But then there's like another natural isomorphism from the dihedral group into S3. We saw that just thinking of labeling the triangle corners and watching what happens to the corners of the triangles is a permutation. So I can think of that. It's just basically saying these two things are the same. They act the same, and you can think of either one whenever you want to work with one of them.
Okay.
That's literally our next topic in here. We will definitely be doing isomorphisms.
Okay. Are there, so, for two spaces, is there only one, like in, like vector spaces, are there only, like, what, is there a unique isomorphism between two spaces? Like,
No, because you could rotate by any,
yeah.
like in a real space, like think Rn, any basis for Rn is gonna be isomorphic to any other basis
For
or,
R.
yeah.
Yeah, for our.
You can just take each basis vector and send it to one of the other basis vectors. And then that defines your, so yeah, so what I would do is if I had a vector space V and a vector space W and I had a basis here of V1 through VK, if I wanted, and somebody told me these two things were isomorphic, so I had some phi that was 1-to-1 and onto, and it preserved structure, then the basis for this thing, a basis for this would be,
also be k-dimensional.
it would also be k-dimensional.
Yeah.
And this phi would be a linear map.
Okay.
And that's what the isomorphism requires here. So these aren't linear probably ever, or there's nothing to be linear because we don't have a combo of operations. We don't have that.
We don't have
vector.
like a binary like set of operations.
Yes, exactly. We only have one, so.
Okay.
I have a question on
Yep.
D.
Yes,
Sorry.
which one? No, it's okay. E, I'm sorry.
D.
D.
So 1 goes to 4.
Yeah.
Sorry.
Goes
Or-
to 3.
Sorry, yeah, 1 goes to 3, which goes to 4. 4 goes to 1, which goes to 4, but.
No, you're skipping. You're going too fast. 4 goes to 1. Oh, wait.
4 goes to 1.
1 goes to.
How does that work?
Wait a minute. I think the first one is wrong. 1 goes to 3. 3 goes to 4. 4 goes to 2.
Oh, you have to go through all of
You
it?
have to go through all of it.
I didn't realize that part.
Yeah, you've got to go through everything in the chain.
Ah.
See if,
Oh,
these right, you just throw something together with order 3, order 5.
So what does that say? No.
The problem is this is a very specific. Let's see. I think you actually have it, but this is things that can be a composition of an even number of transpositions. And I think both these are, so I think that you actually did it.
Okay.
I think
I'll
you
just
did
look
it.
at it again.
Just
and
save
make
it,
sure
save
I
it for
got
after
it.
we talk
Yeah.
about A.
Yeah.
I have a question on
Yes,
this.
ma'am.
I'm a little confused on one.
Yep.
So we can leave right here.
Oh, okay, well, we better talk about number 3 really quick. So, if we're gonna talk about, it's kind of that, Number 3, there's one last thing I need to show you, shit, sorry. That's why I was glad we started. Every permutation can be written as a product of transpositions. So every permutation can be written, and I'm going to show you how to do that. It's another computation, as a product of transpositions. And this is, we'll pick up here. What is that question asking? God, that word is transpositions, evidently. What was the question asking, Sophie?
Oh, it's express the following permutations as products of transpositions and identify them as even or odd.
Oh, okay, cool. So so what you do is, let's just make up 2, select this guy. So if I want to write this as a product of transpositions, I start with the 1, and I swap the 1 with the end element. 1 goes to 2. Now watch this. And everything, these will not be disjoint. Everything's going to anchor off this first 1. So I go 1 to 2, 1 to 5, 1 to 4, 4, and then 1 to 3.
So it's even?
So yes, and it's even or odd based on how many transpositions are in there.
So because there's 4 of them.
It's an even permutation because it's an even number of transpositions. Let's check this out. So let me check that this worked. So 1, where does 1 go? 1 goes to 3. 3 doesn't get touched, right? Where does 3 go? 3 goes to 1. Then where does 1 go?
1 goes
To 4. Does 4 get touched again?
No.
Look how it's coming back. The trick is to work backwards. Did you see how I did that? Like dun, da, dun, da, dun, da, dun. So this is an even permutation, and guess what? If it's just a cycle, it's 1 less. If it's odd number of things, it's an even permutation. If it's an even number of things, it's an odd.
What do you do if you have a function though, or a composition?
Then simplify it down. Then
Get
work.
it to the 1.
Yeah, or break each part of it down. I would first simplify it into nice disjoint cycles and then do this.
So like compute it first.
Yes,
And then do
and
that
then
part?
decompose into transpositions.
Okay.
Does that make sense?
So like basically do what we're doing in 2 and then do the next step of.
Yes.
Right, got it.
Is everybody cool with that? Like how that works?
And you can start with whatever element is first, so if it's not 1, say you have a 2 there, it would be like 2, 3, 2,
Correct.
4.
Yeah, just start at the first element and do the do. And then you can check yourself. If you're like, did I fuck this up? We'll just check it.
Yeah.
Good?
Cool.
Are you almost done with your homework now?
That happens,
Yeah.
right?
Okay, that's what I wanted. I wanted you to have a good weekend. Yes, ma'am. Did you have a question? Yeah, sanity checks. Okay, maybe. Let's see. So that is order 4. So that's order 4, right? So if you raise it to the 4th power, what do you get? If that were 4. What does it mean to be order 4?
Even itself.
No. Bye. Yeah, thank you.
Have a good weekend.
You too. Bye.
Oh yeah, have a good weekend.
Yeah, I have to watch a scary movie, the one I recommended.
Because, so if it's order 4, do I go like 1, 2, 3, 4?
So, no, so where does 1 go? It's 1, 2, 3, 4. 1 goes back to 1. You move ahead 4. So
Oh.
the 4th power of this, the order is the length of the cycle. Because 1 would end up, if you did this 4 times, 1 was back at 1, 2 gets back at 2. So you get the identity.
Okay.
So if you raise this to the 4th power and get the identity,
It's just the identity.
to what power? Yes, and what is that?
Okay.
There you go. Yes, yeah, you can just put epsilon.
So you
Do I still have an have I gotten everything back to you that you've given me?
Yes.
Okay, thank God.
Yeah, that 3rd assignment you gave me is kind of kicking my ass.
It's gonna, I'm not
it's
looking
good.
forward to grading it.
It's because it's all about isomorphisms. It's like, what? It's weird, but
Yeah, let's, maybe get together on Monday or Wednesday of next week, does that
Yeah.
sound good? I'm back in office hours, so,
all good.
sounds good.
Fair
I got an
enough.
appointment on Friday, but
Okay,
other than that,
That's perfect, actually, cause I got some DippyQ stuff to cover,
hell
so
yes. All
I'll
right,
see you
be well.
sometime
my
next
friend.
week.
I'll see you next week, bye.
Also, I dropped some corrections on your book for like.
I saw something happen, cool,
Yeah.
thank you.
That's it.
And then, can I do it, I said I need to check on this one.
Oh, yeah, so let's see, so did you probably wanna compute this first and then rewrite this, that's what I would do, cause this scares me to, like, my brain wouldn't work, I would first compute that and rewrite it,
Okay,
do you know what I'm saying?
yeah,
So I
so
would,
it'd be like one
Yeah.
goes to 4. one goes to
yes,
5.
yes, you kinda just flip these guys, you
Okay.
delete the first one in place and you flip the rest
Okay,
too.
I think I did that in my head.
Okay,
So
that's
still
pretty
could
good.
be correct.
So let's see, so you got 1, 4, 2, 5. So 1 goes to 4, 4 goes to 5. Yep. 5 goes to 2, 2 goes to 3, 3 goes to 1. That looks good. And then I think the other two look great. So let's see, so 2 goes to 1. Wait. What did I do wrong? Wait, 2 goes to 1.
And then 1 goes to
Oh, to 2, yeah, so it's great, yeah, and then the other one has to go to itself, you don't got no other place to send it.
Okay, I just wanted to make sure I
Yeah,
had
you're
that
doing
right.
great,
Okay,
you're doing great, nice,
cool.
cool.
Thank you.
Yeah, thank you. You did so good on that, oh, did I give you your corrections? Yes,
Oh,
or something, no, your homework, I gave you your
yeah.
homework,
Yeah,
right?
it was in homework.
Yeah, you did really good, you're doing great,
Thank
you're
you.
doing so good.
It takes a lot of rereading other theorems.
Yeah, that's
and
good.
Google.
You're kind of a natural mathematician, you really are, no, you are.
I-
It's like, I should shut off this video.
Oh. I don't know, I like numbers, they make sense.
Well